Hello, welcome to this webinar sponsored by the Ocean Observations Physics and Climate Panel. My name is Magdalena ANDRES, and I am a physical oceanographer at the Woods Hole Oceanographic Institution. I have been invited by OOPC to present part 1 on the Gulfstream system. Part 1 is focused on the Gulfstream observations, and a companion presentation, part 2, is focused on modeling. The purpose of this pair of webinars, like others in this series, is to start a dialogue motivated by the following question. What components of a Gulfstream observing system are required to link ocean physics, as observed by the global observing system, to regional coastal systems onshore of the Gulf Stream? A good place to start this conversation is with an assessment of what we already know about spatial and temporal scales of variability in the Gulf Stream system. While I'm serving as the presenter today, this assessment rests on the work of many, many others. Citations and references are collected at the end of this talk on a final slide. The Gulf Stream is a swift boundary current. It is fed by the loop current, which flows out of the Gulf of Mexico, and it flows from the Straits of Florida towards the tail of the Grand Banks, after which it's known as the North Atlantic Current. The Gulf Stream carries warm, salty waters poleward, and on its path, large amplitude meander crests and troughs form, and sometimes pinch off to form warm core rings and cold core rings. Between Florida Straits and Cape Hatteras, the Gulf Stream flows along the edge of the continental shelf, along the continental slope. Beyond Cape Hatteras, the Gulf Stream detaches from the western boundary and flows as a free jet where the large meander amplitudes sometimes form. The Gulf Stream has wide-reaching influence. It's a region of tremendous air-sea exchange. In the wintertime, this is a location where the Gulf Stream, or where the ocean, hands off a lot of heat to the atmosphere as cold, dry, atmospheric air passes over the warm Gulf Stream. The Gulf Stream is also a part of the Atlantic meridional overturning circulation. That is a vertical circulation cell where warm waters are carried poleward and colder waters are returned at depth. It's important to remember that the Atlantic meridional overturning circulation is not synonymous with the Gulf Stream. The Gulf Stream carries both a wind-driven component and this Atlantic meridional overturning component, which is related to density. The Gulf Stream also plays a tremendous role in shelf-ocean exchange processes. Between Florida Straits and Cape Hatteras, these interactions can be direct as the Gulf Stream undergoes frontal meanders, which can upwell nutrient-rich waters directly from the deep ocean onto the outer continental shelf. Downstream of Cape Hatteras, where the Gulf Stream is separated from the continental shelf by the slope sea, most of the interactions between the Gulf Stream and the shelf are indirect. For example, warm core rings that pinch off from the Gulf Stream can impinge on the outer continental shelf and influence the exchange of waters there. Occasionally, the Gulf Stream does undergo such large amplitude meanders that it directly impacts the Middle Atlantic Bight continental shelf, but that's the exception rather than the rule. So the Gulf Stream, one of the characteristics of the Gulf Stream is that it varies greatly in the downstream direction. The current strengthens and deepens as waters are entrained in the current. As a matter of fact, south of New England, the Gulf Stream reaches from the surface down to about 5 kilometers depth as a full water column current. In addition, along its path, the water masses carried by the Gulf Stream vary. Along its route from Florida Straits downstream, the Gulf Stream loses Antarctic intermediate water and it gains upper Labrador sea water, intermediate water, and 18-degree water. In addition, the character of the Gulf Stream path variability changes greatly across Cape Hatteras. Between Florida Straits and Cape Hatteras, meanders are relatively small amplitude, whereas downstream of Cape Hatteras, meander amplitudes are very large and the envelope of the locations where one can find the Gulf Stream is very wide. In addition, it has been noted from observations that Gulf Stream transport anomalies are not coherent up and downstream of Cape Hatteras. Transports as measured in the Florida Straits compared with those as measured between New Jersey and Bermuda do not covary with one another. In addition, the Gulf Stream is challenging to measure. It presents an extreme environment for ships, moorings, and autonomous sensors. For those of you who have tried to take hydrographic casts in the Gulf Stream, you know that it is very hard for ships to hold station in the Gulf Stream. Tall moorings often suffer severe blowdown, getting blown down by 100 or 200 meters by the drag of the currents on the mooring line. And autonomous sensors, like Argo floats or gliders, tend to get swept downstream rapidly or ejected out of the current. In addition, the Gulf Stream is challenging to measure because it exhibits variability over multiple spatial scales. There's localized variability, for example, as observed in thick mixed bottom layers near the Charleston Bump, where the Gulf Stream interacts with the topography. There are regional recirculations where waters are entrained or extracted from the Gulf Stream. And then sometimes there are wholesale north-south shifts of the Gulf Stream downstream of Cape Hatteras. The Gulf Stream is also challenging to measure because it exhibits variability over multiple temporal scales. So transport in the Gulf Stream doesn't exhibit very strong seasonality, but there seems to be a clear seasonality in the formation of rings. Cold core ring formation tends to peak in May, and warm core ring formation tends to peak in July. There's very strong mesoscale variability in the Gulf Stream system, and this makes it very difficult to detect decadal and longer scale variability. And so far, there's no statistically significant decrease observed in the Gulf Stream transport directly as it flows between New Jersey and Bermuda. In addition, high frequency meanders and internal tides are presently difficult for satellite altimeters to resolve, but they exist in the Gulf Stream. For example, there's temporal variability in the amplitude of Gulf Stream frontal meanders as it approaches Cape Hatteras, and those frontal meanders exist in about 3 to 5 day period, which satellite altimeters presently can't resolve. And finally, the Gulf Stream is challenging to measure because it's a very deep reaching current. South of New England, as mentioned before, the Gulf Stream reaches from the surface down to about 5 kilometers depth. And just by way of comparison, the limit of Argo floats presently is 2,000 meters depth. The limit of spray glider measurements is about 1,000 meters depth. And the limit of velocity measurements from shipboard ADCPs is about 600 meters depth. So there's a lot of the Gulf Stream that's difficult for us to observe directly. So as we think about the requirements for observing ocean physics at ocean boundaries, a good place to start is to think about the global observing system. So the global observing system includes sea surface height measurements from satellite altimetry, sea surface temperature measurements from satellites, measurements of temperature and salinity profiles from Argo floats. There are full water column repeat lines from the WOS program and now the GoShip program in the region. And then there are repeat XBT lines, which tell us about the temperature profiles in the upper ocean. The regional coastal systems in the Western North Atlantic comprise or include the following. There is an OOI Pioneer Array, which is presently located south of New England. It will remain there through the fall of 2022. In spring of 2024, the plan is to relocate the Pioneer Array to the southern mid-Atlantic bight, just north of Cape Hatteras, onshore of the location where the Gulf Stream separates from the western boundary. There are tide gauges along the coast, and some of these provide us with very long records of variability. Indeed, tide gauges that span the Gulf Stream have been used to reconstruct transport since the early 1900s, and it's found that the transport since 1982 has likely been weaker on average than that during 1909 to 1981. And this is estimated by using tide gauges that span the Gulf Stream and the Florida Straits. In addition, There are NDBC buoys throughout the region. And there are HF radars, high frequency radars, along the coast. And from Cape Hatteras southward, some of these high frequency radars are close enough to the Gulf Stream so that the Gulf Stream falls within their footprint. I'm calling out here 3 of these radars, Hattie, Duck, and Core, which are near Cape Hatteras and are well positioned to see the Gulf Stream right where it's veering away from the continental shelf across the isobaths and into the open ocean. And here are several websites which are useful resources for accessing the data from some of these regional coastal systems. In addition, there have been some recent process studies in the area. Line W was a 10-year study from 2004 to 2014 of the deep western boundary current south of New England, with 2 moorings falling within the Gulf Stream, and then regular hydrographic cruises across the Gulf Stream. So those, even though the focus of that study was on the deep western boundary current on shore of the Gulf Stream, those data are still useful for helping us to characterize the Gulf Stream, especially the deep part of the Gulf Stream. And then the Peach program was a 1.5 year study from 2017 to 2018 of the processes that drive exchange between the open ocean and the shelves near Cape Hatteras. So in terms of a Gulf Stream observing system, there isn't really a single coherent system, but there are components that together might be thought of as a system. So the Oleander program is a long-running program where a commercial vessel is outfitted with a shipboard ADCP that measures velocity profiles beneath the ship as it does its weekly round trip between Bermuda and New Jersey. These measurements have been made since 1993, and temperature profiles have been measured with XBT since the late 1970s. So this provides a really valuable long-term in situ record of Gulf Stream variability. In the Florida current, we have cable-based measures of daily transport with regular calibration cruises since the early 1990s. So these daily transports are a very useful way of monitoring the Gulf Stream. There's a big distance between Florida Straits and the Oleander line. And recently, we have gotten more information about the Gulf Stream between these 2 locations from the Gulf Stream Glider program. So since 2015, there have been about 36 missions. These missions, the glider swings back and forth across the Gulf Stream. So there are 250 Gulf Stream crossings and 30,000 profiles of properties, temperature and salinity from the surface to 1,000 meters depth. And these cover the 2,000 kilometer distance along the Gulf Stream between Florida Straits and the region south of New England. So by combining information from the Oleander line, from the Florida current cable measurements, linking those with information from the Gulf Stream gliders, we certainly can learn about the Gulf Stream, but we have not really resolved all of the temporal and spatial scales of variability in the Gulf Stream with these existing assets. So if we think about what would make an ideal observing system for the Gulf Stream, we can think of several recommendations for Gulf Stream observing. The first recommendation would be to acquire more high horizontal resolution, directly measured velocity sections across the Gulf Stream, similar to those that we presently get from the Oleander line. We could make use of existing shipboard ADCP data from the academic research fleet's crossings of the stream. Those are existing sections, and it's just a matter of accessing them and making them broadly available. One could outfit more commercial vessels with shipboard ADCPs. An important part of this would be to build the pathway from ship to model so that these directly measured velocity data from the subsurface ocean could be better used in forecasting. And an important part in building that pathway would be to include the oceanic and atmospheric modeling communities along the way. So these recommendations together could be thought of as developing a global subsurface velocity program. And this would benefit not just measurements in the Gulf Stream, but it would benefit measurements in many boundary currents, which are difficult to resolve with current observing system assets. And then finally, if we have ships making shipboard ADCP measurements of velocity, it's really important and useful to collect complementary underway data streams. For example, weather measurements, PCO2 measurements, flow-through measurements, like from a TSG or other underway systems. Another recommendation would be to consider a Gulfstream complement to the new Southern Mid-Atlantic Bight Ocean Observatories Initiative Pioneer Array site. This is going into the water just north of Cape Hatteras in a region that's very interesting, in a region where the spatial correlation scales are very short, and it would be very helpful to have measurements within the Gulfstream at this location. It's important not to forget the deep Gulf Stream. Remember, the Gulf Stream south of New England reaches to 5 kilometers depth. When we're making upper ocean measurements, we're really missing 3/4 or more of the Gulf Stream. So to measure the deep Gulf Stream, it will be necessary to entrain new technologies to observe. This could include deep gliders, it could include deep Argo, or it could include some other bottom moored instruments. And another recommendation for the Gulf Stream observing really has to do with how we assess and evaluate and interpret the observations. It's important to remember that the Gulf Stream, especially downstream of Cape Hatteras, wiggles and meanders. So it's important to evaluate the Gulf Stream in a stream coordinates frame when examining this current. Especially downstream of Cape Hatteras, Eulerian averaging tends to smear the properties and structure of the current. So while I have this slide up with some of the citations and credits, I'll also briefly go through some of the logistics for the various observing components, coastal and Gulf Stream. So the OOI Pioneer Array, the Ocean Observatories Initiative Pioneer Array, is funded by the National Science Foundations through the Large Facilities Office. Its operational budget is on the order of $8 million per year, but it's important to remember that this budget includes ship time to service the arrays. So presently there are 2 cruises per year to service the arrays with multiple legs for each cruise. High frequency radars along the coast of the US are between Florida Straits and Cape Hatteras are supported by SACURA. SACURA holds a 5-year cooperative agreement with NOAA to serve as a US regional association in the US Integrated Ocean Observing System. Different organizations are responsible for different sets of the radars. For example, there are 4 radars near Cape Hatteras, which are jointly run by the University of North Carolina, Chapel Hill, and the Coastal Studies Institute of East Carolina University. And so for those 4 radars, the operational budget is about $140,000 per year. Other regions along the South Atlantic Bight, where the high frequency radars see the Gulf Stream, include some radars run by these HF radars that see the Gulf Stream are operated by the University of South Carolina, Skidaway Institute of Oceanography, and the University of Miami, with new installations being put in by the Florida Institute of Technology. The Gulf Stream gliders, the operational budget for running those is about $400,000 per year. This is funded by presently by NOAA and ONR, the Office of Naval Research. In the past, it's been funded by National Science Foundation, and there's now a pending proposal to continue that funding through NSF. The Oleander program is also funded by the National Science Foundation through the Physical Oceanography program that supports the ADCP measurements, the thermosalinograph measurements, and an auto launcher for XBTs, with the XBTs supplied by NOAA. The operating budget for the Oleander is on the order of $300,000 per year. In addition, there are separate programs to measure PCO2 and CPR, continuous plankton recorder. So in closing, I think an observation that I'd like to make is that there's a lot of observing going on in the coastal ocean, and there's a lot of observing going on in the global ocean. But it really is important to focus on these boundary currents, which are difficult to observe and relatively sparsely observed compared to the rest of the ocean, even though they're very important because they exist at the place where the deep ocean meets the shallow ocean, and this is a place where really interesting physics are happening.